Today we're going to look at the three-dimensional figure, the sphere. We're going to look at the volume and the surface area. So the formula for volume is 4/3 pi r cubed. And the formula for surface area is 4 pi r squared. Now, volume measures 3 dimensions, and we have the 3. Area measures 2 dimensions, and we have the 2. Okay? So here we have a sphere. And if we take a look at this sphere, its diameter is 10. Well, the formula doesn't use diameter, so if the diameter is 10, what is the radius? 5. All right? I'm trying to switch to blue. There we go. So volume would be 4/3 pi 5 cubed. Actually, 5 centimeters cubed. Okay, so 5 cubed is 125. 125 times 4 is 500. So 500 pi cubic centimeters is our exact answer. What would the approximate answer for this be? Yeah, it's second and the third key.
523.6.
You are all correct. 523.60 cubic centimeters. Awesome.
What is it?
523.6. Okay, surface area. How would you describe surface area of a sphere? When would we use it?
In the real world?
Sure, in the real world. Or contextually. What do you think, Jack?
So like, know how much paint you would need to paint?
A ball? Did y'all notice at Target that they painted the balls out front like Pokeballs?
They did?
The Target in Peachtree City? I laughed out loud when I saw them. Huh? I did. LOL. Alright. Okay, so you're right. That is exactly what it would do. So if we were trying to put a covering on a basketball and we needed to know how much, I don't think you truly use leather anymore, but leather to cover the basketball, that would be area, right? Okay, so in this case, if our radius is 5 to find the surface area, we would do 4 pi 5 centimeters squared, and so that's 25 times 4, so the exact answer would be 100 pi square centimeters. The approximate answer you don't need your calculator for, it would be, good, 314 point,
159.
so 159, so it would round to 16. There we go. Nice job. Okay, we have a little definition here, and this is important to be able to work with some of our sphere problems. A great circle. When we see the words great circle, what that refers to is a circle whose center is the same as the center of the sphere. So this is a great circle because the center of this yellow circle is also the center of the sphere. Now we have an indefinite number of great circles in a sphere. We could have one that looks like this. We sliced it this way, where the center was the same. Okay, now what would not be a great circle? Here's an example of one that is not. You see that this is a circle that I could cut out of this sphere, but the center is not the same as the center of the circle. So the purple one is a non-example, counterexample. A blue? What color is that to y'all?
Blue.
All right, we'll call that blue then. Violet. I like it. All right. So, we are given that the radius of a great circle of a sphere is 25 pi square centimeters, and you're asked to find the volume. So, you try this one. So, think about what variables I need to find the volume. Solve for those first. many people got excited when they saw the radius was 5 because it's not the same as the first one. So you didn't have to do any work. So the exact volume is the same, and the approximate volume is the same because the radius is the same. Any questions? Okay, so here, if you're given the volume of a sphere is 972 pi cubic inches, and you're asked to find the diameter of the sphere. Okay, so we know that volume is 4/3 pi r cubed. So when we solve this, it's going to give us the radius, we double it, and we have the diameter. Okay, so the first thing we're going to do is cancel pi, divide both sides by pi, and then to solve, we're going to multiply by the reciprocal. And so we get r cubed equals 729. And then we get real excited because this is one of our perfect cubes that we memorized. It is. So the cube root of 729 is 9. So if the radius is 9 inches, then the diameter would be 18 inches. Are we good? All right. The next example. This looks like ice cream. Anybody hungry?
Yes, very.
Mine, I think, is probably chocolate with peanut butter.
I know it's a snow cone.
What flavor is yours?
My favorite ice cream flavor?
Yeah.
I like cookies and cream.
Cookies and cream. That's a good one. Yeah. All right. So, here's a composite figure. So what we have here is a hemisphere and a cone. Well, a hemisphere is half a sphere. So instead of being 4/3, it is 2/3. So if we were asked to find the volume of this composite figure, we would have to add the hemisphere with the cone. How do we find the volume of a cone?
1/3.
1/3.
Times pi r squared times pi.
Very good. Okay, so we have to do both of these. Now if they just ask us for the hemisphere, then. All right, so when we're thinking about a hemisphere, let's see. Let me steal the circle drawer. All right. I missed. So close. Okay, so here's a hemisphere. All right, when we think about surface area, we need to think contextually. So if it's in terms of a word problem, what exactly are they asking us for? Are they just asking us for this little round dome part? Or are they asking us for the dome plus the base? Okay, so generally with surface area, if it's contextually, if it's a word problem, it's the dome plus the base. So it would be half of 4 pi r squared, so that would be 2 pi r squared. So this gives us the dome part plus the base. What is the base?
Oh, yes, clear.
The base is a circle, so its area would be pi r squared. And you'll never have to know this, but we could just add it together and have 3 pi r squares.
Wait, wouldn't it be pi r 4? Oh, you're adding.
No, Brad.
No, you're so
Okay, the last thing I want to go over before I give you class time to get started on your homework, whoop, whoop, is what happens if we change our dimensions. So if we double the radius, what effect would that have on the volume? So whenever you're talking about changing one of the dimensions by a multiple, think about the formula. Where does that dimension go? What happens to that dimension? Well, in volume, that dimension gets cubed. So if we double the radius, what effect does it have on the volume? What is 2 cubed?
8, so 8
It
times.
becomes 8 times greater than the original volume. Do y'all see that? So doubling the radius would increase that volume by a factor of 8. think of what happens to that dimension in my formula. Okay, so we have some questions out of our book. We do have some composite figures like number 23. Number 23 is a hemisphere that's been scooped out, cut out of a cone. That one's a little better, a little clearer in your textbook today. Alright, so it's the geometry book, page 383, and these are our problem numbers. They're the same ones that are written on the board, it's the same ones that are written on your calendar, and the same problems that are posted to the website. You have the rest of class to start working. If you'd rather just come take a picture of a book, there's one open on the front desk, or you can pull yours out.
Okay.